I'm going to deal with carbon. Carbon and how it burns. Carbon as an element is arguably, actually there's no argument about it, carbon is the most important element. Most of the chemistry we do is to do with carbon chemistry, and let's get to grips with it. So first, whereabouts is carbon on a periodic table? If you look at a periodic table, group 1, group 2, group 3, it's there, carbon. It's in group 4. Now group 4 means 4 electrons in the outermost energy level. An atom of carbon and an atom of carbon. I've just picked 2 images off the internet. This one, 6 protons, 6 neutrons, 6 electrons. Similarly here, 6 protons, 6 neutrons, 6 electrons. And the arrangement of the electrons is 2, 4, consistent with the idea I need you to learn that the outermost energy level electrons is the same as the group number. So group 4, 4 electrons in the outermost energy level. Those 4 electrons are the ones that will be used in bonding, and that's why carbon makes 4 bonds. And we sometimes say carbon has a valency of 4. Right, so pure carbon. This is pure carbon. That is a lump of graphite. That is pure carbon. Diamond is pure carbon. And graphite is very different to diamond. Yet both of those will be made up of carbon atoms only. So pure forms of carbon are diamond and graphite. And there's a new word which we want to teach you. It's that word there, that word allotropes. Now, allotropes are different forms of the same element. So if you've got carbon, diamond and graphite are made of carbon atoms. They're pure carbon variants, and we call them allotropes. So the most common allotropes are graphite and diamond for the element carbon, different forms of the same element. There are others that have been discovered since, but when I first started teaching in 1985, the syllabuses only knew about diamond and graphite. Now since then we've got a few more. Now the few more are important, but your syllabus requires you to know diamond and graphite in detail, and it might ask you questions about the others, but they will only be questions about the covalent bonding, etc., that happens within them. They won't specifically want you to know the structures of anything other than diamond and graphite. So when we dig it out of the ground, graphite, as I've shown you, see that graphite looks like that. Photograph of graphite. That is raw, rough diamond. And they're both very different. And they're different because the arrangement of the carbon atoms is different. They're both made of carbon atoms. They're both made of exactly the same thing, carbon atoms. This is an element carbon and that is an element carbon. This element carbon form is cheap, that element carbon form is expensive. That element carbon form, diamond, is very, very tough. This isn't. This flakes off in layers. You can even see the layers. If I hold it up close, maybe you can see the layers, and certainly you can see the layers here. You can see the layers running across, and those layers come off very easily. Not so with diamond. With diamond, very tough material, probably the toughest material that we have on Earth, is very different to graphite. And the difference is down to the arrangement of the atoms. So let's have a look. Here I have a model of diamond. There I have a two-dimensional picture of diamond. I've annotated with my own notes because I couldn't find anything that was good enough. And what I need you to know is that every carbon atom is joined to four others in a huge three-dimensional framework, which we can call a lattice, and that lattice is massive. This is just a teeny weeny bit of it. The smallest of diamonds will have within it billions of atoms arranged like this. Can you see all of these little green straws represent a covalent bond? These black blobs represent a carbon atom. Each carbon atom, like look at that one in there, that one, is bonded to four others. Now obviously the outside ones are not, because we need to carry the structure on. We need to continue it on, and then they would be connected to four others. It's only the very outside ones, which there are not many of those in a real diamond. The billions of atoms inside the diamond are all bonded to four others. And those four other bonds are covalent bonds, and they're strong bonds. Look, each carbon atom is bonded to four others, covalent bonds, all strong bonds, making diamond the toughest of all known materials. One diamond is therefore one huge, gigantic molecule. And there's no weakness anywhere. That's what makes it so tough. Three-dimensional lattice of carbon atoms. Remember that word lattice? Just a three-dimensional repeating pattern. That is definitely three-dimensional, it's repeating, etc. So, you need to know that structure. For diamond, you've got to know that structure. Now, very difficult to draw, so they don't ask you to draw it very often, but they draw it for you and ask you questions about it. So, get to grips with how the carbon atoms are arranged to make up diamond. Now, graphite. Graphite is made up of the same carbon atoms that diamond is made of, but the arrangement is different. Look, within the layers there, you've got hexagons of carbon atoms, and the carbon atoms are bonded to just three others. Not like diamond, where the carbons in diamond were bonded to four others. Here, the carbons are bonded to three others. To make three bonds, they use three electrons, the outermost electrons. So there's one electron left over. That electron is free to move around within the layers. So you've got this layer, and there's three electrons moving around within it. Each layer is millions of carbon atoms big. And the layers are huge, millions of carbon atoms big. Each one's got a spare free delocalized electron, and so there are millions of free delocalized electrons in every layer, and they will be responsible for conduction of electricity. See, diamond does not conduct electricity, but graphite does conduct electricity because there are free electrons in the layers. Now, the layers themselves, look at it that way on, the layers themselves have strong covalent bonds. So three of them, three strong covalent bonds, but they're strong, very strong nevertheless, and they hold the layers quite firmly. The layers are tough. Now, like we used to talk about carbon fibre, and I've got a carbon fibre badminton racket, and the layers give you strength in a particular direction. In that two-dimensional plane, you can get strength. And my badminton racket is made so that when I smash, the forces are huge and the shaft will not break. Yet, my racket is really light because it uses a small amount of material in order to make the racket. So carbon fibre has been around for a long time, and it uses these graphite layers. Now between the layers, these white straws represent weak attractions. So there are weak attractions between the layers, and there's strong bonds in the layers themselves. Now, this is a model we use. We wave it around and show to classes. And that there is the two-dimensional diagrams you find in books, and they might give that to you on an exam and ask you questions about it, or sometimes they ask you to draw that. And now what I need you to know is there are strong bonds within the layers. I need you to know there are weak intermolecular forces between the layers. Very similar to when I discussed molecules with you in the bonding topic. There were strong bonds in the molecules, but there were weak intermolecular forces between molecules. It's that kind of idea. The layers are only weakly attracted to each other. So the layers slide over each other very, very easily. Look, I can show you. Here I've got some paper. Here I've got that lump of graphite. And if I do that, that is the layers coming off onto the paper. That's what pencil is made of, graphite. Graphite comes off onto your paper from your pencil. It's the layers of graphite. Each layer comes off millions of carbon atoms onto your paper, and it looks like pencil. That is the layers of graphite coming off that blob. If you keep doing that, that will go down just like pencil lead. If you keep writing with pencil, it goes down because the layers are coming off, there's less material left, and the pencil leads get smaller and smaller and smaller. So the layers themselves are really tough. Between the layers, they slide over each other really, really easily. And that will explain a lot of the properties that we'll get onto in a minute. But you need to understand that. That's the structure of graphite. Each layer is a large molecule. The layers slide over each other. So, huge molecules are the layers. Between the layers, weak attractions. The layers slide over each other very easily. So, this slide, important slide. Diamond, toughest material, as all carbons are firmly held in place. In contrast, graphite. Layers slide over each other easily due to weak intermolecular force of attraction to the layers. So graphite is a good lubricant. The best oils for cars are graphite included within the oil. The graphite, if it gets between metals, say my hands are metals, then if you put graphite in between them, the metals will slide over each other much better, much less friction with graphite between them, because the layers of graphite really go over each other really very easily. The really expensive oils are graphite included within the oil, and they're called synthetic oils, and they're expensive. Diamond is never, you can't use diamond as a lubricant. Diamond, really, really strong. So it's used in drill bits. If you want to drill through really tough rock, you've got to use something even tougher. And what we use are diamond drill bits. So bits have metal and they put diamond encrusted within them. Cheap, teeny weeny little diamonds, but nevertheless those cheap little teeny weeny diamonds will cut their way through the toughest of rocks, because the diamonds are themselves even tougher than the toughest of rocks. So what about melting points? Well, diamond hasn't got any weak bonds. In order to get that to boil and melt, you've got to break covalent bonds, and to break covalent bonds takes a large amount of energy, very high temperatures needed, like 4,000 degrees. And And then when you've got 4,000 degrees, the diamond will turn into gas. It will go straight from solid diamond to gaseous diamond. Gaseous diamond is single atoms on their own as a gas. And that only happens over 4,000 degrees. Now, 4,000 degrees is a huge temperature to get in a laboratory. The kilns in our art department that are used to fire up pottery, they reach temperatures of 1,000. We need temperatures of about 4,000 to break these strong covalent bonds. Well, graphite, very good at conducting electricity. It conducts electricity because of the free electrons that there are within the layers. Diamond does not conduct electricity because there are no free electrons in the whole structure. All the 4 outermost electrons are used in 4 bonds. So there are no free electrons, and therefore diamond does not conduct. Graphite has high melting points and boiling points because in order to get it to melt, you've still got to break the 3 strong covalent bonds within the layers. The layers have to be separated, and only then will graphite melt. And again, that takes a huge amount of temperatures, about 4,000 degrees even on graphite, just like diamond, because you're having to break those strong covalent bonds. Okay, so those properties, you should be able to relate those back to the structures. Let's go back. Let's go back to allotropes. Now, I think in around 1992, somebody found the existence of this. I know it looks a bit like a football. It's called Buckminster fullerene. They found carbon can exist like this, in kind of balls. They were called buckyballs. The proper name is Buckminster fullerene, which is a bit of a mouthful, and that's why people were calling them buckyballs. Now, they found that you could have carbon existing like this, with 60 carbons. 60 carbons making one molecule. That's one molecule. That's a small molecule. Small molecule, diamond and graphite are huge molecules. Diamond and graphite we call macromolecular because they are so very, very huge. When we start talking about millions of atoms in one molecule, like in a layer of graphite, that makes it macromolecular. Diamond, macromolecular. Buckyballs, simple molecular, small molecules. Now, since then, there have been all kinds of, since 1992, when buckyballs were discovered, people have found that you can get bucky tubes. If you just elongate this out to a tube with more carbons linking the curved ends together, etc. But that is an allotrope. So allotropes, diamond, graphite, Buckminster fullerene. So Buckminster fullerene is a very recent isotope. Sorry, not isotope. The word is allotrope, not isotope. That's a mistake. Allotropes are different forms of the same element. So diamond, graphite, Buckminster fullerene are allotropes. Right, so don't worry too much about these buckyballs. Just worry about diamond and graphite. Right, carrying on then, what do you need to know? Well, that word I used, macromolecular. Macromolecular. Now, if we start with the idea that a molecule is defined as a collection of atoms covalently bonded together, then there are small molecules like buckyballs or hydrogen, water, methane, ethanoic acid, and up to about 100 atoms, I would say they're small molecules. More than 100, up to like thousands, I would say are large molecules. Now, proteins, plastic polymers are examples of large molecules. But they're not gigantic. When we get to gigantic molecules, we're talking millions of atoms big, all covalently bonded together. Then we use that phrase macromolecular. And you need to know about diamond and graphite are examples of macromolecular structures. And sand is another one. Now, sand will have a structure a bit like this. Diamond, except instead of all the atoms being carbon, sand has some atoms being silicon and some atoms being oxygen. Sand is silicon dioxide and it's macromolecular. You only need to know about those three. There are not huge numbers of macromolecular structures in our world. But for GCSE, you need to know those three: carbon, diamond, and sand. And whenever we have macromolecular structures, to melt them, you have to break the strong covalent bonds inside the huge, gigantic molecules. And that always takes a lot of energy, and that always leads to high boiling points, high melting points as a consequence. So sand has a very high boiling point, very high melting point, because you have to break the strong covalent bonds between the silicon and oxygen atoms within the silicon dioxide, which is the common chemical name for sand. So macromolecular structures, you need to know about them. We don't mention them in bonding and structure when we teach ionic, covalent, metallic bonding, because we don't want to confuse you. But you do ultimately need to know about them, and I'm mentioning them here now for you to take on board. So this slide should live within the bonding and structure topic. It should live within covalent bonding, and within that we should talk about huge molecules are possible, and they're called macromolecular, and they have the difference to normal covalent. Normal molecules that are small molecules, they're different because the boiling points, melting points are really huge, because you're having to break covalent bonds, which you normally do not have to do if you've got small molecules. Right, so let's talk about burning carbon. Well, the cheapest form of carbon we have is this thing here. I don't know if you can see that in the dark room. This is graphite. Sorry, it's not. Graphite, we didn't have many lumps of graphite. So this is charcoal. Charcoal that I've got here is like 95% carbon. So the cheapest form of carbon is charcoal. And if I burn it, I should find that the carbon within it joins with oxygen. Carbon and oxygen together make carbon dioxide. Now, if I've got loads of oxygen, I'll get complete burning, complete combustion, and I'll get just carbon dioxide. If I don't have enough oxygen, I'm going to get not complete combustion, and I'm going to get some carbon monoxide. Let's do it, and then you can see. So, let's perhaps turn this on. So, roaring flame. Now, you will see some sparks because pieces of this graphite will come breaking off and burn in the flame. Can I get you closer? Now this is the kind of reaction that's going on in a barbecue. If you buy charcoal briskets that you put on your barbecue and you cook on your barbecue, then this is the reaction that's going on. If I blow, I hope you can see. When I blow, the burning is better, because by blowing, I'm providing oxygen. And when I'm providing oxygen, the carbon joins with oxygen, making carbon dioxide. And that's burning. That's almost complete combustion. Now, let me take you over here. Back to my PowerPoint. So, if carbon is burnt in not enough oxygen, if you don't have enough oxygen, then what you get is you get a yellowy, orangey coloration, which you should be familiar with that kind of colour. Of a Bunsen burner flame with the air hole closed. Now, when you have that kind of colour in flames, then that is not enough oxygen. When you don't have enough oxygen, then you're going to get carbon monoxide. If you've got enough oxygen, like when I was blowing it, you just get carbon dioxide. So what you need to know is that if carbon's burnt with plenty of air, you get carbon dioxide. Look, that's complete combustion, you just get carbon dioxide. And if you don't have enough oxygen, then you get not complete, incomplete combustion. And there's the equation for not complete combustion. And you need to be able to write both. And you need to know that carbon dioxide is a greenhouse gas. And you need to know that carbon monoxide is a poisonous gas. It will have a greenhouse gas effect too, but the thing they ask you about carbon monoxide is, why is it poisonous? So let's deal with that. So normally the lungs, when you breathe in, hemoglobin inside your blood, hemoglobin will pick up oxygen molecules. And the oxygen molecules will be transported around your blood to wherever your body needs them. Like your brain needs it, then the hemoglobin will deliver oxygen, drop the oxygen off, and then the hemoglobin molecule will be free again. It'll go back to the lungs, pick up more oxygen, go and deliver it somewhere else, like your big toe, and then it'll drop the oxygen off there at your big toe, and then go back to the lungs, and so on. And that's what hemoglobin does. That's the job of hemoglobin. Now, carbon monoxide interferes with that. When you breathe in carbon monoxide, look, carbon monoxide molecules are a similar size to oxygen. So when you breathe in carbon monoxide, your body thinks that it's oxygen. Your hemoglobin picks it up and makes carboxy hemoglobin. Now, when carbon monoxide joins with hemoglobin, once it's joined, it never lets go. The hemoglobin takes the carbon monoxide to your brain or your big toe, tries to drop it off, and it can't. It stays firmly bonded to the hemoglobin. And that means that hemoglobin cannot do the transportation of oxygen we need it to do to keep a healthy body running. And if you keep breathing in more and more and more carbon monoxide, and you keep tying up more and more and more hemoglobin molecules, eventually, if you don't have enough hemoglobin molecules to transport the oxygen, then eventually you would die. You need oxygen to live. Oxygen starvation is how you would die. Now, just to let you know what the symptoms are, just so that if it ever happens to you that you're in an environment where something is burning, the first symptom is headache. You start feeling a headache, and your headache turns to tiredness if you keep breathing it in, and you have no... Yeah, my phone went off there for some reason, so I'm picking up again. So I don't know how far I got. I think I got as far as saying carbon monoxide molecules are a similar size to oxygen. And when you breathe in carbon monoxide, your body thinks, that's oxygen. Your hemoglobin molecules will try and pick up the carbon monoxide, well, they'll try and pick up oxygen that they think is oxygen, but it is in fact carbon monoxide. And when the hemoglobin molecules pick up carbon monoxide, that carbon monoxide binds really strongly and never lets go of the hemoglobin. That means that that hemoglobin is not able to do the important job of transporting oxygen to wherever your body needs it. And if too many hemoglobin molecules do that, then your body's not getting the oxygen in the transportation of oxygen that's needed to function properly. And it starts getting ill. And if you keep depriving your body of oxygen because there's not enough hemoglobin, then eventually you'll die of oxygen starvation. Now let's go through the symptoms. The symptoms are, first, you get a headache. Then you start feeling tired. So headache, tiredness, you feel nausea, and you might sit down. And if you keep breathing in the carbon monoxide, you'll drift off into a sleep, and then you will die. Now, luckily, there aren't many people that die of carbon monoxide poisoning, but it's a sad fact that people do die of carbon monoxide poisoning, like with faulty boilers in their homes, and people do die of carbon monoxide poisoning when you hear these horror stories of people in their garages that turn their engines on inside their garage, build their garage full of carbon monoxide, and sit inside the garage as you've got these carbon monoxide fumes, and the large quantities of carbon monoxide eventually kills the people, and they've done it deliberately because that's how they've committed suicide. So, yeah, it's sad business. Anyway, look, carbon monoxide is poisonous. You need to know how it's poisonous. That doesn't seem to be wanting to go any further. Anyway, I think I've explained it. I'll see you next time. It's headache. You start feeling a headache, and your headache turns to tiredness if you keep breathing it in, and you have no some reason. So I'm picking up again. So I don't know how far I got. I think I got as far as saying carbon monoxide molecules are a similar size to oxygen. And when you breathe in carbon monoxide, your body thinks, that's oxygen. Your hemoglobin molecules will try and pick up the carbon monoxide, well, they'll try and pick up oxygen that they think is oxygen, but it is in fact carbon monoxide. And when the hemoglobin molecules pick up carbon monoxide, that carbon monoxide binds really strongly and never lets go of the hemoglobin. That means that that hemoglobin is not able to do the important job of transporting oxygen to wherever your body needs it. And if too many hemoglobin molecules do that, then your body's not getting the oxygen in the transportation of oxygen that's needed to function properly. And it starts getting ill. And if you keep depriving your body of oxygen because there's not enough hemoglobin, then eventually you'll die of oxygen starvation. Now let's go through the symptoms. The symptoms are, first, you get a headache. Then you start feeling tired. So headache, tiredness, you feel nausea, and you might sit down, and if you keep breathing in the carbon monoxide, you'll drift off into a sleep, and then you will die. Now, luckily, there aren't many people that die of carbon monoxide poisoning, but it's a sad fact that people do die of carbon monoxide poisoning, like with faulty boilers in their homes, and people do die of carbon monoxide poisoning when you hear these horror stories of people in their garages that turn their engines on inside their garage, build their garage full of carbon monoxide, and sit inside the garage as you've got these carbon monoxide fumes, and the large quantities of carbon monoxide eventually kills the people, and they've done it deliberately because that's how they've committed suicide. So, yeah, it's sad business. Anyway, look, carbon monoxide is poisonous. You need to know how it's poisonous. That doesn't seem to be wanting to go any further. Anyway, I think I've explained it. I'll see you next time.